Hello guys, good morning. Welcome back to the problem solving session of electrochemistry. Okay, like you all know, we are doing some problems based on electrochemistry, which is helpful, which has been asked in previous year JEE NEET exams. Okay, so let's start with the session. So the first question we are going to see here is this. Find the equilibrium constant. Find the equilibrium constant for the reaction given. For the reaction given, and the data which is given over here is given over here is the reduction potential of Cu plus Cu2 plus Cu2 plus to Cu it is given, Cu2 plus to Cu plus it is given, indium plus 2 to plus 1 and plus 3 to plus 1 it is given, right? So we need to find out the equilibrium constant, which is Kc for this reaction. Okay, so let us understand the question first. And the question is, you see, this question has been asked in IIT JEE 2004, right? So reaction is given, and we have ions in this reaction. But it's not like solid is present into this. Okay. So how do we do this question? So first of all, you see the reaction which is given here and the reduction potential, because you see all these are reduction potential. Okay, for Cu2 plus, it's not standard, but it is reduction potential. Okay. So now based on this, if I write down the reaction here, that reaction would be Cu2 plus 1 electron gives Cu plus. This is the first reaction, and its E value is given, so we can easily find out delta G. Okay. Similarly, we can write down the other reaction, which is In 2 plus 1 electron In plus. Okay. The another reaction is this In2 plus converts into In3 plus. To get this reaction, what I'll do, I'll write down the reaction so that this In3 plus will be on the right hand side. So for this one, this In plus gives In3 plus 2 electron. Okay. Now with the help of this 3 equation, we'll get the cell equation which is given, right, in the question. So we need to obviously eliminate this In plus because it is not present here in the reaction. So for that, what I'll do, I'll add these two in order to cancel out this electron. Okay. So what I'll do, I'll just, because you see, obviously we cannot cancel out this electron, because in order to do that, this In plus will still be present in the reaction. So we'll add simply this reaction so that this In plus will get eliminated. Okay. So when we add this to reaction, what we get, you see, we get here In2 plus gives In3 plus electron. Now delta G of this reaction would be, for this first reaction it is delta G1, for this reaction it is delta G2, and for this reaction it is delta G3. So this delta G is equals to what? We can write delta G2 plus delta G3. Okay. Now with all these delta G value we'll find out, and then we'll find out the net equation. So delta G for this would be, okay, see, one thing is missing here. This should be E naught, because you see these are E naughts, so it should be E naught. And since we have to find out equilibrium constant, so obviously E cell will be 0. So we need to find out E naught cell of this reaction. So it is understood in this question that this should be E naught. Okay. So all these delta G is delta G naught, standard state. Delta G naught. Okay. So delta G1 is equals to what we can write? Minus NF E cell. Okay. E naught cell. So minus NF E naught cell, N value is 1. And F is this, will write minus 0.15 E, sorry, 0.15 F. Okay, this is delta G1. Delta G2 is equals to what? Minus IN2 plus 2IN plus is this. So 0.4, it is 0.40 Faraday. And for this one, it is IN plus 2IN3 plus. So it should be plus of this, right? So minus of 0.42 Faraday. Now for this reaction, delta G naught would be, we'll just add these two. So 0.40 F plus minus of 0.42 F. So it would be minus of 0.02 Faraday is the delta G for this. Okay, so this E naught value we got. Now we have to find out for this one. So what I'll do, I'll just add this two reaction, 1 and 2. This two reaction will add. So when we add 1 plus 2, what we get, we see. So we are not concerned with the reaction, because reaction obviously it would be this. Cu2 plus In2 plus gives In3 plus Cu plus, and electrons gets cancelled. Remember one thing, if you have done everything correct, then this 2 electron will get cancelled. Okay, or by multiplying some number, but this has to get cancelled. If it is not getting cancelled, it means you have done something wrong. So when you add this 2, we are concerned with the only delta G naught of the net reaction, which is this, and that would be the addition of this plus this. So we can write here delta G1 naught plus delta G naught, and that would be this minus this, so it will be minus of 0.17 Faraday. Okay, minus of 0.17 Faraday. Okay, now for this reaction, we'll write down delta G naught is equals to minus of 2.303 RT log Kc. This Kc we need to find out. So we'll substitute all the value and we'll get the answer. So Kc is equals to, approximately you get 10 to the power 10 when you solve this. I'm not solving this, okay? All the expression I have written, the value you have to substitute here, and you have to get the answer. Kc is 10 to the power 10. Right, so I hope you have understood this. It's an easy question. Just all the data is given. You need to find out delta G naught for this. Because if you find out delta G naught, then you can write down the expression delta G naught is equals to minus 2.303 RT log Kc, and then you can find out K, the equilibrium constant. Okay? Yeah. Next question we see. Try this one. Now in this it is given, we have taken a saturated solution of AgBr, Ksp is given. If 10 to the power minus 7 moles of AgNO3 are added to 1 liter of the solution, find conductivity. Okay. So in AgBr solution, we have added 10 to the power minus 7 mole of AgNO3. We need to find out the conductivity of the solution in terms of 10 to the power minus 7 Siemens meter inverse. Okay. Okay. Now when we have 10 to the power minus 7 molar AgNO3, we have 10 to the power minus 7 molar. Okay. 10 to the power minus 7 molar AgNO3 this will reduce the solubility of AgBr because we have, see the question is, we have taken a saturated solution of AgBr and in this AgBr, AgNO3 added into the 1 liter solution of it. So since we have AgNO3, we are adding into the saturated solution of AgBr, 1 liter we have taken, right? So this reduces the solubility of this AgBr, right? Because of the common ion effect. Okay. So if I write down the Ksp of AgBr, that will be concentration of Ag plus and concentration of Br. Okay. 10 to the power minus 7 molar we have added. So Ag plus concentration is what? S plus 10 to the power minus 7, because this is the what concentration we have added. If solubility is S, so S plus this, and Br minus is S only. Okay, so solubility decreases, so we can neglect okay, so it is given 12 into 10 to the power 14, right? AgNO3 added to 1 liter solution of it. Okay. First of all, you see what we need to find out, and then we'll go back to this concentration part. That would give a proper idea. The total conductivity, if I write down kappa, that would be because of the movement of ions, right? Because of the movement of ions. So what all ions we have here? What all ions we have here? We have Ag plus ion present. We have KNO3. We have KBr, right? Sorry, we have NO3 minus ion, Ag plus and Br. These three ions are present. Ag plus, Br minus, and NO3 minus. These three ions are present. So we can write the lambda, this equals to the conductivity of Ag plus, we can write, right? The conductivity of Ag plus the conductivity of Br minus plus the conductivity of NO3 minus. Okay, NO3 minus. So we need to find out the solubility of AgBr in AgNO3 solution. Okay. So the concentration of Ag plus will be this, S plus 10 to the power minus 7, because this we have added, and the concentration of Br minus is S. Ksp value is given, which is 12 into 10 to the power 14. And this, when you solve this, okay, solubility will be very less because of the the concentration of AgNO3. Presence of Ag plus will decrease the solubility of this. So we can write, if you neglect this, S into 10 to the power minus 7, and this solubility becomes 12 into 10 to the power, I think this should be minus. This should be minus here. 12 in 10 to the power minus 7. This is the solubility we get. Okay. So Br minus concentration is this. Ag plus concentration is again this. And NO3 minus concentration is 10 to the power minus 7. All these things, if you substitute here with lambda, if you find out, you'll get the answer. Okay. But in this thing, like in this one, I think that's what you see. It is a mistake in this question, guys. So you see in this one, this is lambda, it is given, right? But this is what? The unit is what? Unit is molar conductivity. If you look at the unit, it is molar conductivity. And we need to find out this S Siemens meter inverse, right? It means, how do we get from unit? Let's understand with the unit. Per mole. And this you have to convert in S meter inverse. So how do we get that? You have to divide this by mole per liter, means concentration you have to divide over here, because liter is nothing but meter cube. Okay. 1 liter is given, so mole per liter. Now this mole per liter is what? 1000 meter cube, right? So we can write here 10 to the power minus 3 S meter inverse we get. Okay. So whatever the concentration of ion, because all these terms are molar conductivity, not the ionic conductance, right? It is not the ionic conductance, it is molar conductivity. So molar conductivity you have to convert into conductivity, right? So this term, if you multiply this by concentration, then you will get this. So for all these, let me just correct it. The question is missing here. It is the conductivity, kappa is equals to the conductivity of all ions That is what we need to consider of all ions. Okay. So this thing, if you multiply it by concentration, suppose lambda naught m of Ag plus is equals to into, if you multiply by the concentration of Ag plus, you will get kappa of Ag plus. Concentration of Ag plus divided by 10 to the power minus 3, that we need to do. Okay, so concentration of Ag plus we can calculate from this. We'll substitute it here, right? So let's calculate this for Ag plus, then probably you'll understand. Lambda m naught for Ag plus is given 6 into 10 to the power minus 3 into Ag plus concentration we have calculated, and that is 12 into 10 to the power minus 7. Remember here also it's 10 to the power minus 14. It is not 10 to the power 14. Obviously that value is too huge, right? That is not possible. 10 to the power minus 14 it is there. So solubility is 10 to the power 12 into 10 to the power minus 7, right? So this is the concentration of Ag plus and the concentration of Br minus. Okay. In fact, if you find out the total concentration of Ag plus, right, that would be S plus 10 to the power minus 7. So if I write down here, concentration of Ag plus would be S plus this. So we'll have 13 into 10 to the power minus 7. Concentration of Br minus, that is S only, 12 into 10 to the power minus 7. And the concentration of NO3 minus would be what? 10 to the power minus 7. 10 to the power minus 7. Okay. Now this concentration we have to substitute here. Ag plus concentration is what? 13 into 10 to the power minus 7 divided by 10 to the power minus 3. This 10 to the power minus 3 I have divided here so that the unit will be, the unit of this term if we calculate, this will be Siemens per meter. For this unit I have taken this 10 to the power minus 3. So you see the question is in 10 to the power minus 7, and that is what we are getting. So it is 78 for Ag plus. Similarly, we can find out for Br minus and NO3 minus, and we can add those. Okay. So for Br minus, what do we get? 12 is the concentration, right? 12 into 8, that is 96. So K for kappa for Br minus is 96, and kappa for NO3 minus is the 7 into 1, that is 7. So when we add all those, so the conductivity of all ions is 78 plus 96 plus 7, and that would be 104, 104 plus 78, 182 Siemens per meter. This is the answer of this question. Okay, so like it takes some time because of the confusion in the question. In the question it is lambda naught is given. It should not be lambda naught, but it is delta, it should be delta m naught, molar conductivity. And how do we get this information? We get this information from the unit. So from this unit, you have to get this Siemens centimeter meter inverse. So accordingly, you have to do that change. Okay. So with this KSP thing, we'll find out the concentration of ions. Got it? Correct. Next question you see? See this question. A solution containing 1 mole per liter of each ion, which is given, is being electrolyzed by using inert electrode. By using inert electrode, the value of standard reduction electrode potential is given. The value of standard electrode potential is given. We need to find out. With increase in voltage, the sequence of deposition of metals on cathode. Okay, so we know at cathode reduction takes place, right? And all these ions you see, they have given the reduction potential because it is getting, it is oxidation potential, it is getting oxidized, right? Oxidation potential it is. This one is also oxidation and this one is also oxidation, right? So on deposition of cathode means it has to get reduced. And we know the one which has maximum value of oxidation potential will have the minimum value of reduction potential. Okay, so Ag to Ag plus, the oxidation potential is plus 0.80. Okay, so reduction potential of silver is minimum and magnesium is maximum. Silver is minimum and magnesium is maximum. But what happens? Magnesium reduction potential again, you see guys, there is a correction here also. In the question, it is written standard electrode potential, means reduction potential it is given. But the notation is oxidation. Okay, so it is standard reduction potential we have to assume, because in the question it says standard reduction potential, right? All these are standard reduction potential. So fine, let it be. So standard reduction potential is maximum for Ag, right? And it is minimum for magnesium, it seems, right? If you see the value here. But the standard reduction potential of water, if you know, that information you should have. The standard reduction potential of water is 0.83, right? SRP of H2O is minus 0.83 volt. So for magnesium, you see the value of magnesium, the standard reduction potential is very less, right? And it is talking about what? Mole per liter, each of this being electrolyzed in this. A solution containing 1 mole per liter means the solution of water we have, aqueous solution we have to assume, correct? Since magnesium reduction potential is lower than to that of water, it means magnesium won't get reduced. Okay, so all those metals which has higher reduction potential than water will get reduced. And the easier reduction will be for silver, first of all, because silver will have maximum value of reduction potential, and then we'll have Hg, and then we'll have copper. So this is the order. We have Ag, Hg, Cu, but here magnesium won't get reduced because the reduction potential of magnesium is lower than to that of water. Got it? So answer for this question is option D. Okay. Again, one correction, it should be given like this, Ag plus 2 Ag. Then it is reduction. Should be like this. But we are going with the question written in the question, reduction potential. So we are taking reduction potential. Correct. Next question. A metal wire M dipped into the solution of 40 ml of 1 molar solution. The solution of M2 plus ion has a potential of this millivolt, right? How much volume of water will be added to the metal ion solution so that when it is combined with standard hydrogen electrode, no current flows? Okay, so it means what? For no current, for I to be 0, it means E cell should be 0. There is no EMF, right? E cell should be 0. We know hydrogen electrode, the EMF is 0, right? Standard electrode potential is 0. So if we have to reduce this M to M2 plus, the reduction is given. So we have to make this E cell, you have to make this as 0, right? So concentration of M2 plus, it is given in the question, is 40 ml solution, we have 1 molar. 1 molar 40 ml solution. So the question is, how much volume of water must be added to the metal ion solution so that when it is combined with standard hydrogen electrode, no current flows? Okay, so for no current, we must have change in EMF is equals to 0, right? E cell must be 0. And for that, what we need to do, if I write down the E cell Nernst equation for the cell, right, that would be E naught cell minus 0.0591 divided by n log of the concentration term. But you see, a metal wire M to M2 plus, if it is goes, its potential is given, that is 0.029 volt, right? And for hydrogen has a potential. So we are assuming this has reduction potential. So its reduction potential is this. So oxidation potential is negative of this. So minus of this oxidation potential if I write down. So basically the reduction potential M2 plus to M is given 0.029, and for hydrogen the reduction potential is 0, right? So this one has more reduction potential, so this will get reduced, right? So this metal will be the cathode and this will be the anode. Cathode and anode. Okay, so now when you write down this, so the equation will be, we'll have H plus in the numerator and the square we have here, and Cu M2 plus in the denominator. Okay, okay. So in this question you see again, E cell, this should be 0. For 0 current, this should be 0, right? So E cell will be what? E cathode minus E anode. Cathode reduction potential we know, it is 0.029 minus 0 minus 0.0591 by 2 log of H plus concentration is not given. Okay, so suppose I'll take it as 1. Let's see what happens. Divided by the concentration of this M2 plus when we add this. So we add this concentration. So what we can write, the concentration initially it was 1 molar. So 1 molar into 40. So 40 millimoles. So we have 40 millimoles initially. So 40 divided by X plus 40. So I'll write down here V plus 40 divided by 40. V we need to find out. So this would be almost, if I take this 0.03, so this side it is 1, so log 10 is equals to log of V plus 40 by 40. So 400 is equals to V plus 40, right? So V is equals to around 360 we are getting. The closest value is 350 because that the approximation we have made. Okay, so what I did here, see, first of all, the concentration of H plus is not given. So we have taken it as 1. Okay, 1 concentration of H plus we have. Initially, we have 40 ml 1 molar solution. Means number of millimoles is 40 millimoles of this ion we have. So now what happens, we have 40 millimoles of this and we have added V ml of water into this in order to make E cell 0. So concentration now it becomes what? 40 divided by V plus 40. This is the concentration of that ion. That is what I have substituted here. The concentration of this ion is 40 divided by V plus 40. H plus is 1, so we get this. E cell is E cathode minus E anode. Cathode is this ion because its reduction potential is more than to that of water. So this minus this equals to this. Okay, because for hydrogen it is 0. So when you solve this, we'll get log of V plus 40 by 40 is equals to log 10 because this value is 1 approximately. It is suppose 0.3. It is also 0.03. So that will be approximately 1. So log 10 is equals to this. So when you solve this, you'll get approximately 350 I'm getting 360 here with approximation 360 ml. So we'll take 350. So this is the answer for this question. Concentration of H plus is not mentioned. I have assumed this as 1 because it is not mentioned. Okay, next one. Okay, 14th one, you see, a current liberates this gram of hydrogen in 2 hours. Okay, the amount of copper deposited at anode during the electrolysis of this by the same amount of current. Okay, so we know when the same amount of current passes through, equivalent will get deposited, right? So equivalent. So number of equivalents of hydrogen is equals to the number of equivalents of copper. So number of equivalents of hydrogen is what? It is the given mass divided by equivalent mass of hydrogen. This mass we need to find out, and equivalent mass of copper is what? 63.5 divided by 2 because n factor is 2. So when you solve this, the mass of copper is equals to 0.504 into 63.5 divided by 2. So 0.25, that would be 1 by 4. So 15, 16 around we'll get. Around 16 approximately. Right, so the mass is approximately 16 gram will get deposited. Okay, 15th one you see. The solution of this in water is electrolyzed using inert electrode. The product at cathode and at anode. Okay, so this actually you should know that what is the product we get in this case. Okay, it's a theoretical concept, the 15th one. Solution of Na2SO4 in water is electrolyzed using inert electrode. So we have what? You have Na2SO4 plus water. So what all ions are present into this? We have H plus, Na plus present, which moves towards the anode, SO4, 2 minus, and OH minus present, which moves towards the cathode. Okay, so which ion gets oxidized or reduced, and then we can understand the product of the electrolysis. Okay, so Na plus and H plus, you should, if you know the electrode potential of Na plus and H plus, you can understand this. Okay, but with only electrode potential, we cannot say all the time that this would be the product. Okay, because sometimes what happens, sometimes over potential also comes into the picture, right? So in that case, the things will be different. It is not same as we expect, right? So Na2SO4 and K2SO4. If you see the Na2SO4 and H2O, if you see the electrode potential of Na plus and H plus, we know for Na plus the electrode potential is 0. Sorry, H plus electrode potential is 0, and for Na plus the electrode potential is, okay, electrode potential is in negative, right? Because it is on the top. So H plus has 0 value, Na plus has negative value. So obviously H plus will get reduced. It has more reduction potential. It gets reduced, right? And it forms what? It forms H2 gas. So H2 will definitely comes out in this reaction. Okay, H2 definitely comes out in this reaction. So we can easily eliminate option B and D. right? Solution, this water is electrolyzed using inert electrode. So what happens here, this at anode, at cathode, what happens? 2H plus converts into plus 2 electron converts into H2 gas. This happens. At anode, it is, in this case, we have two possible cases here. The concentration, when we have very low concentration, then OH minus will get oxidized and it converts into half of O2 plus H2O plus 2 electron. If you multiply this by 2. Okay, half of O2 plus H2O plus 2 electron. At low concentration. At high concentration, sulfate ion will get oxidized into S2O8 2 minus. Okay, so in this case, since the concentration thing is not mentioned, whether it is high or low, right? So we won't consider the high concentration. If it is high, it must be mentioned. Okay, the answer for this question is the product at cathode is H2 and the product at anode is O2. That is the only answer we have. Again, one more thing you can consider. We got this point that whether it is at cathode, what reaction takes place, because H plus has more reduction potential, so this will get reduced. So this is at anode, this is at cathode. So obviously at cathode, H2 is coming out, hence the option is C only. A is not possible. B and D we have already eliminated because H2 is not present. Okay, hence the answer is C. Fine guys, thank you. Next class we'll see some more challenging problems. Till then, take care. Bye bye.